Hello, my name is Alejandro Salas, and this is a code walkthrough of my graph project for my data structures class. So the requirements for this assignment was to create a graph with at least 20 nodes and 20 edges. And at first I was really struggling with this project because I wanted to create this graph on my own from scratch. And this was in C++, and I realized that this was not going to be possible by the due date. So I decided to search for a library that allowed me to create a graph easier. And I found this Python library called NetworkX that allows me to do just that. This library is super easy to use, and I'm glad I chose it because it allowed me to grasp the concept of graphs even more and allowed me to have a finished project. So I'll go through the code. So I imported NetworkX, which is the library, and matplotlib to actually get an image of the graph. And in line number 4, we're actually creating the graph itself. And the way you add edges and nodes in NetworkX is super easy. You just have the graph that you named, and then you just simply add edge. And the first attribute is the node that you want to connect to the second node you want to connect. And you can also add the attribute of weight, which is basically, for this example, how long it is. So the longer it is, it has a direct correlation with the higher weight. And for this project, I'm going to show the reference picture that I use for my graph. So this is what I used as a reference for my graph. The numbers are pretty much illegible, but I promise there's 20 nodes. This is 1, and here's 20. And this is how I connected all the edges, how I managed to figure out where to connect it and how to decide the weights of each edge. So as you can see here, this is the first outer ring, which is shown here. This is the outer ring. And then this is level 2. I'll show the code in a sec. Level 3 is these, and then level 4 is the pentagon in the middle. So if we go back to the code, we can see level 1, level 2, level 3, and level 4, all with their respective edge and nodes connecting to each other, and also the weights. And now moving on to the algorithms that I use to sort through this graph. For the 3 algorithms that I use were shortest path. I also use Dijkstra's path and A-star path. These all 3 algorithms are to find the shortest path, but I wanted to see how they would differentiate if they did. So let's go ahead and run the actual code. So we can see that using the shortest algorithm, we got the path 1, 8, and 20. And while not using the shortest path, while using Dijkstra's and A-star path, we got a longer path. And now I'm going to show the picture of my graph. This is how it looks. Every time I run this project, it creates it a little bit different. It takes a different shape. So it goes random. So let's see. Now it's a different shape, and we'll run it one more time, and I'll get a different shape. But something that I wanted to show was the actual algorithms and how they can be altered by the criteria you give them. So for example, if I add the attribute of weight, meaning that it actually considers a weight in the algorithm, when I run this project, you can actually see that Dijkstra's path actually took the shortest path, which is 1, 8, and 20. And if we go back to the picture, we can see that 1, 8, and 20, this is 8, I promise, this is 8. We can see that 1, 8, and 20 is actually the shortest path. And this is the same for A-star, the algorithm A-star. And I believe this is because this is a really simple graph, but the more complex the graphs are, the more implementation of these algorithms you can have, and then you can decide which one's the best one for that application. And then I draw the graph and save it to the figure, which can be, sorry about that, which can be seen here again. This is my graph. Every time I run this project, I get a little bit different, but all the nodes and edges are the same. Well, that's been my project and my explanation of the code. Thank you so much for your time and attention.